All right, welcome back. We're going to do the third hand rule now. The third hand rule is definitely the most interesting one. And the third hand rule applies to either charged particles going through a magnetic field just by themselves, not in a wire, or it deals with charged particles going through a wire and then placed in the presence of another magnetic field. Because if a charged particle going through a wire creates a magnetic field. If you put a magnet around it, obviously those two magnetic fields are going to interact and they're going to force that wire to move in a direction. So the third hand rule says that it makes sense if a current carrying wire induces a magnetic field around it, should feel the same force if it is brought near a separate magnetic field. So here, in this example here, right, we have a wire. And we're going to run, let's say we run electrons through this wire, and this wire is going into the board. So you have to look at this from a three-dimensional perspective. This wire is going into the board, and the rules for the third hand, the third hand rule says that you're going to point your thumb in the direction of the current flow, electron flow, proton, alpha particle, whatever it is. It's electrons, so I'm using my left hand. And your fingers are going to point in the direction of the magnetic field, always from the north to the south. So in this example here, I would point my thumb into the board, and then I would orient my fingers so they're pointing from the north to the south. So I'm actually going to have to twist them around this way, like that. Oh, that's awkward. And your palm then faces in the direction of the magnetic force. So in other words, there's my thumb going into the board. There's my fingers going from the North Pole to the South Pole. And my palm faces upwards. So in other words, that wire is going to feel a magnetic force pushing it up. Okay. So that one, that's, now here it is how here's another way that you can depict that down here. Is the wire is going into the board. So thumb into the board, magnetic fields from north to south, so that way, and my palm is pointing up. So therefore, the magnetic force on this wire is going to be up. So the wire is going to want to be pushed up. Okie dokie. That's the basics of it. Oh, and we're going to have to make up a whole bunch of examples here because that's not sufficient. So let's do a bunch of examples on the third hand rule. Let's say that you have a magnet here, North Pole, South Pole. Now let's say you have a wire going this way. So your wire is going to the right and you're running electrons through it. To the right. So electrons are going to the right. And there's your magnetic field. So your thumb is going to point to the right. Your finger is going to point from the north to the south, so upside down here. And which way is my palm facing at this point? My palm is facing towards me, so it's out of the board. Out of the board. So the answer to this question is simply this. Or out of the board, or out of the page. All right, let's do another. There are lots of permutations you can do of this one. Let's go with a magnetic field south, north, and this time the electron flow, as you can see, is out of the board. So what does my thumb do? My thumb points out of the board, like this, out towards me, looking right towards me. Which way are my fingers going to go? From the north to the south, so I have to tilt my hand like that. And which way is my palm facing? Up. So this one, the magnetic force, or F subscript M, magnetic force, is up. So this one, the wire will be forced up. Okay, be good with that. Now, there's in the assignment you have, there are a lot of applications of this. Let's say that you have this. And this time, we're not going to go with an electron, we're going to go with a proton. So if it's proton, if it's positive, then you are going to use your right hand, and your right hand is going to point towards the right. And what are your fingers going to do in this case? They're going to point into the board. Your finger's going to point into the board. And which way is, oh, the answer for everything is up. I should have done another one. So in this case, the proton will be deflected up. The proton is going to go into the magnetic field and it will be deflected up. Now, just to get ahead of ourselves a little bit, if you go on to lesson 18, I think it is, if I extended that magnetic field up here, once the proton gets to this point, now you're gonna have to change your hand configuration because now the proton is moving up. The magnetic field is still going into the board, and so which way is it deflected at this point? It's deflected to the left, as you can see right here. It's deflected to the left. So if it gets deflected to the left, it goes like this. Now what's happening here? At this point, it's moving to the left, so your thumb needs to point to the left. Your fingers are still pointing into the board. Which way is your palm facing? Down. So it's going to go down. Ooh. And then when it gets to here, what happens that time? It's going down, fingers into the board. It's going to be deflected to the right. So as you can see, it ends up moving in a circular path, which is has some applications in itself. In terms of your assignment, there are questions like use the third hand rule. A question might be something like, let's say here's the Earth, and we know, you should know, that this is the magnetic south pole of the Earth. It's opposite to the geographic south pole. They're not exactly in the same place because the geographic poles are based on the rotation, the axis of rotation, whereas the magnetic south pole and north pole are not based on that. So anyway, this is the magnetic south pole of the Earth. It's up where we think the geographic north pole is. This is so let's say, so the magnetic field lines go from the north to the south, out this way, in this way. So let's say I'm sitting here in the middle of the Earth, and I have an alpha particle, a helium nucleus, and I project that helium nucleus up towards the North Pole, or the geographic North Pole, or the magnetic South Pole. So it is an alpha particle, and it's projected along the surface of the Earth in that direction. And the question is, what is the magnetic force on that alpha particle? Well, for starters, I have to use my right hand because this alpha particle has a charge of +2. I'm going to point my thumb up. So my thumb's going to point up like that. My fingers are going to be from the north to the south. So my fingers are going to be directed from the north to the south. Now, what's the problem here? The problem here is that they end up being like this. The alpha particle is going up from the north. My fingers point up towards the South Pole, from the north to the south. And so they're parallel. They're parallel at this point. So what is a trick question? What is going to be the force on this alpha particle? There's going to be no force. It's just going to go straight. Okay? But let's say I decide to take that alpha particle and project it to the east. So I'm in the middle of the Earth, I project that alpha particle to the east. So now we have something that we can, there's going to be a magnetic force on that alpha particle. So my thumb points towards the east. My fingers point towards, from north to south, to the south pole of the magnetic south of the Earth. And which way is my palm facing now? It's pointing towards me, so it's out of the board, out of the board. The answer to this question is out. In other words, if you have an alpha particle and you're in the middle of the Earth and you project it to the east, that alpha particle will be forced away from the Earth. Yeah? Now, what if I change that to an electron? And I did the same thing. If I did an electron going to the east, I would use my left-hand rule. And what would the electron do? It would be forced towards the Earth. So it would be forced into the Earth. So hopefully that clears things up for those kind of questions where you got a charged particle in a magnetic field. Which way is it going to be deflected? And remember, they must be perpendicular. They can't be. If they're parallel, there's no deflection. If they're perpendicular, that's a maximum deflection. And if they're at an angle in between 0 and 90 degrees, then there's partial deflection. Okay, I hope that clears things up for the third hand rule. Actually, let's just go right on and do the next page, because this is the mathematical application of the third hand rule. You've got two formulas you're going to learn here. First one is this here: Fm, magnetic force, equals I, current. L, the length of the wire. B is the magnetic field. B is magnetic field strength, and it's measured in Teslas. And sine of theta. So sine of theta means the angle if it's perpendicular or parallel. Because if it's sine of 90, in other words, it's a 90-degree angle, you're going to get the maximum amount of force. If it's zero, if sine of zero, what's the sine of zero? Zero. So you get no magnetic force. Okay, so then you can go down and look at these two questions. They're pretty straightforward. A piece of wire that is this long is placed in this magnetic field at this angle. If that's the force on it, determine the current in the wire. Pretty straightforward. I, L, B, sine theta. And we're looking for the current. I is the current. I equals Fm over L, B, sine theta. And then it's just a matter of plugging those numbers in. L, B, sine of 67, and you get an answer. The answer for this question is 0.45 amperes. All right. And then it says determine the amount of charge that flows through the wire in this many seconds. This is based on the formula for electrical current. So this is the formula. I equals Q over T, and we determine the amount of charge. So we're solving for Q. So it's just Q equals IT. I is 0.45, T 7.1 seconds. We get the answer, which turns out to be determine the amount of charge, which turns out to be 3.2, right? 3.2 coulombs. That's a lot of charge. Okay. Good. So that's one of the formulas. The other formula, the one that you'll probably use more often, is this formula here. Magnetic force equals Q, the charge, times the velocity of the particle, times the sine of theta. And again, it's a pretty straightforward formula to use. There are no examples. There are no examples of this. Oh, yes, there is. Why did I miss it? Okay, there's an example here. Example 3 says if an alpha particle has a charge of plus 2, so therefore Q equals 3.2 times 10 to the negative 19 coulombs. If an alpha particle moves at 1.2, the velocity is 1.22 times 10 to the 4 meters per second through a 23 Tesla magnetic field. Determine the force it will experience. And it says it's perpendicular. So if it's perpendicular, then it's automatically 90 degrees. You don't even have to put the sign in there, because the sine of 90 degrees is 1. It's 1, and therefore it's irrelevant to the question. Well, it's not irrelevant, but it just means you're going to get the max amount of force. Fm equals QVB. I'm not even going to worry about the sine of theta. Plug the numbers in, and you get an answer of 9.0 times 10 to the negative 14 newtons. Okay, so hopefully that clears things up for the third hand rule. Again, you might have to watch this video or some other videos a bunch of times, because these hand rules are difficult to explain over through video. They're much better live. You get a much better feel for them. So that's all she wrote for that one. And I'm going to make another lesson for the next concept. Actually, we're going to kind of skip. Oh, lesson 18. We're going to do lesson 18 coming right up. See you soon.